very excited to be here with you today. As a quick introduction, my name is Daniel Mazar, and I'll be your host for this webinar. I'm responsible for customer success and sales operations at Maya, and I'll introduce Maya in just a moment, but my role is basically where I'm leveraging my electrical engineering background to support Maya's clients across North America on complex engineering and digitalization challenges. So I'll be hosting, reviewing your questions, and ensuring that we have them answered and are moving through with the flow of the presentation. The presentation itself, we're very excited to have with us Richard Ozaki. Richard is a thermal engineer with Siemens Digital Industries Software. He's based out of California, so it's earlier in the morning for him. He has many years of experience in using not only Flowtherm XT, but additional Siemens tools. In particular, he's a specialist when it comes to electronics. Any areas that we're looking at in terms of thermal consulting or areas related to Siemens tools to solve some of these challenges, Richard is really the guy, and we're very lucky and excited to have him with us here today. Before I pass it on to Richard, just a few other items to share. As I mentioned, this webinar is being hosted by Maya HTT. Maya is a leading provider of digital engineering solutions and a top global partner for Siemens around the world, in particular Siemens Digital Industries Software. Maya's history is in aerospace, but we've been working within multiple industries on complex challenges, especially around electronics and cooling over the last 3 decades. We've seen immense growth around the challenges and adoption in relation to the increase in electrification and the resultant improvements or requirements around cooling itself. And we've been privileged in working with clients around the world on these cutting edge problems. On top of that, today we're covering just a small subset of our expertise in relation to electronics cooling. And again, we'll start off with the fundamental session, but there's a lot more in terms of areas where we're able to provide support, guidance, and strategic consulting. These areas, you can see them on the screen itself, but range all the way from product design, validation, even manufacturing and looking at things in service. We've seen tremendous interest in multiple applications, whether we're looking at AI applications or being able to capture data related to something that's already in the field and turning it to relevant information, or ensuring that there is a strong, coherent digital thread throughout all different areas of engineering design, and then the whole R&D process. So there's a lot more we can talk about, but really just wanted to let you know that if you have questions in other areas that we're not covering today, please don't hesitate to send those as well. As I mentioned, though, today we really will be going into the electronics cooling series and starting off with the fundamentals of electronics cooling. So with that, I will pass it off to Richard, who's going to take it away from here. All yours, Richard.
All right, thanks, Dan. So yeah, good morning, good afternoon, everyone. Welcome to this hands-on simulate series with SimCenter Flowtherm XT. I'm not actually going to be showing too much of Flowtherm today. Really, this part 1 is really going back to basics and covering some of the fundamentals of electronics cooling. What's important to know? Where does the problem start and end? And this is, this can be applied to any electronics thermal engineering that you might want to do, and the things that you need to keep in mind before you dive straight into, selecting heat sinks or placing fans. Let's go back to basics, do some hand calcs, and really understand the problem at the source. So as Dan mentioned, this is part 1 of a series of 4. They're going to be 1 per week. So next Tuesday, there'll also be another session. Today, as I mentioned, we're talking about the fundamentals. Next week, we're going to be talking about what's important to model and consider with IC packages. And then zooming out a little bit, week after that, we're going to be talking about PCB level thermal analysis. And then the week after that, we're going to be talking about thermal test and validation as well. So after you've done all your simulations, how does that all tie together with physical testing, and how do we, complete that feedback loop to get the whole thermal picture? All right, and I hope you can join us for all of these sessions. The link will be the same, yeah, we look forward for you to learn more about the process and the tools that are available. So let's talk about temperature and electronics. So starting from the left, let's talk about some of the environmental effects. So you can see on this pie chart, this is data from the US Air Force, what's the most common modes for electronics failure? And you can see 55% is down to temperature, okay? So if the electronics get too hot, the chips will burn out, the silicon will fail. You know, you've got very, very delicate transistors on the sort of micron or nanometer scale within your packages, and if they get too hot, they fail. Okay, and second to that is vibration. So with temperature and vibration, you're talking 3/4 of all electronics failures. You know, and that's doubly important with military applications where you've got very, very high ambient temperatures that you need to dump the heat into. Okay, so then the next piece of the puzzle is the performance loss. If your device gets too hot, then there are self-sustaining mechanisms within modern electronics to either restrict functionality or slow down the clock speed, so your device isn't going to operate as it was designed because it's too hot. Yeah, this is a mechanism for self-preservation. And until the device cools down, you're not going to see that performance come back. And the worst thing is, you know, when you've got that sort of yo-yoing between those two performance modes because of temperature, you want to avoid this at all costs, as it can really affect the performance of the electronics. And then finally, you have reliability. It's been shown very clearly, the closer and closer that you get to the maximum allowable junction temperature in your devices, then the rate of failures absolutely goes through the roof. It's exponential. So the cooler that we can keep a device, the longer it's going to last, the more sustained performance you're going to see, and ultimately, you know, less warranty or field failures you're going to see. So it's a very, very important part of modern electronics design, as we'll see very shortly. Okay, so high temperature components have the high possibility to fail. You know, and you open any modern electronics these days, and there'll be some sort of thermal engineering in there to extract the heat and maintain performance and lifetime of that particular device. So with that, Dan, let's ask poll question 1, please. It's just a yes or no.
Excellent. Just getting that set up, Richard. Bear with me 1 second. All right. So it should be on your screen now, everyone. Again, very simple yes or no question. Have you had any thermal-related electronics failures? Yes or no? we'll give it another 5 seconds before closing it up. So we have a lot more we'd like to cover. Great. So with that, just to do a quick sharing, Richard, 68% of our attendees are saying yes, they have seen it. So if you could just comment quickly on how that relates to what you're seeing in industry, and with that, we'll keep going onward.
Yeah, absolutely. Like I said, modern electronics, which are in everything, you know, with the IoT revolution, there will be some sort of mechanism in there. It can be as simple as a piece of extruded aluminum just to spread the heat away from the chips, you know, down to full, you know, heat sinks, vapor chambers. Modern electronics are so high performance in such a small package that you need to consider thermal somewhere. So I'm not surprised that people have seen electronics failures due to thermal. All right, carrying on. Okay, so let's talk about the main problem. Where does the problem start and end with electronics? So the hottest part of any electronic system is what we call the junction temperature. The junction temperature is the temperature of the silicon or the semiconductor within the IC. That's what's doing the switching. That's what's performing the calculations, and the logic goes through. That's what we call the junction temperature, and it's always within a chip. Okay, if you open up your computer or your phone, you'll see a board with a bunch of chips on it, and inside the package, the chip itself is very, very small, on the orders of millimeters or smaller, and that's what's actually getting very, very hot. Okay, and for sort of you know, consumer grade electronics, I would say 120 degrees C is on the upper end of the maximum allowable junction temperature. Any hotter than that, and you know, you're going to start seeing significant failures. So, you know, I would say even below 100, you need to keep those junction temperatures. And as we zoom out away from the chip, there's various other electronics items that are designed not only for electrical conductivity, connectivity, but also for thermal dissipation as well. So these chips are mounted on a board. That board might be one of many in, say, a server or a telecom system. That server is probably one of many within a data center. And then you need to finally get that temperature out to the ambient. And, you know, I mean, a hot day in Phoenix, Arizona, you can easily see 40 degrees C or 125 degrees Fahrenheit. That's very common. And electronics need to operate, you know, from sort of Siberian winters all the way through to summer in Saudi Arabia. And that's a wide range of ambient temperatures that you need to dissipate that heat towards. Okay, and that heat is dissipated via conduction, convection, and radiation, and we'll touch on these very shortly. But how easily the heat finds its way towards the ambient determines what the temperature rise is. Okay, so as I mentioned, hottest and the coolest points, and everything else has to fit in between, and it comes down to material selection, thermal strategies as to how hot each of these stages are going to be. So let's talk a little bit about current thermal management state of the art. I've just picked 4 products that I think are quite interesting, that I'm sure most of you will have one of at least, you know, modern smartphones. Let's start with the Samsung Galaxy S10 Android device. I've opened it up here because you can see this little copper little bar on the left-hand side. This is a heat pipe. This is a very thin sub 1 millimeter heat pipe within the Samsung Galaxy S10. Now this device, or this cooling strategy, is designed to move heat away from the processor. So this is running a Qualcomm Snapdragon processor, move it away from the hotspot towards the top of the device where there's a bit more metal casing, where the heat can spread a bit more. What's interesting about this heat pipe is its orientation, right? So if you hold your phone the way you normally do, that's how it's designed to operate, right? If you hold your phone upside down, it's going to perform differently because heat pipes use gravity assist to move the two-phase vapor towards the top of the device and then return it as a liquid. Okay, so if you're hammering the 5G, you're charging your phone and you're watching, you know, a 4K video on YouTube, you might see a peak power dissipation of about 4 watts on your device. Now, this 4 watts, it will not be sustained steady state. You know, if this ran at 4 watts constantly, it would run out of battery in about 5 minutes. Okay, so all the values you're going to see on the power, this is the peak power dissipation of each of these devices. Okay, so that's something I thought was quite interesting with a modern smartphone. Some of you may be into gaming, okay, and you've seen the new NVIDIA 3080 GPUs that were released last year, and these have a peak power dissipation of about 350 watts. Okay, and what's interesting about this one is that you got a range of different cooling methodologies here. Okay, so on top of the actual GPU, there's a vapor chamber. Okay, that's used to spread the heat. Then the vapor chamber is actually connected to some heat pipes. Okay, then you have these heat sink fins, which are spreading the heat even further. And then you've got 2 fans either side, which are using a push and pull methodology to dissipate the heat into the surrounding air. Okay, and when this is mounted in a computer case, one side has got these openings to push air out of the case, and the other side is just recirculating air within the case. So some interesting things that happen to dissipate 350 watts, which is actually pretty significant and is probably more than the actual CPU power load, as is the case with sort of high-end electronics for gaming these days. Very, very, very power intensive. Next one, this is the one I'm most impressed with, the Apple MacBook Air, the new M1 just released last year. So what Apple did was they didn't try and put out the fire that is these other two, right? What they did was they went and designed their own CPU based on an ARM architecture. So moving away from Intel chips, which were on the order of maybe 40 watts, right? They designed their own CPU, which only dissipates 10 watts. So by keeping the same chassis, it meant they didn't need a fan any longer. So this is completely silent, no moving parts, and runs much cooler with a longer battery life because they went to the source of the problem and fixed and designed their own CPU to dissipate much lower heat. So really, really powerful. And this is only version 1, right? So this year or next year, there's going to be another one coming out. I'm sure we'll see smaller, slimmer, more power efficient, longer battery life, lower power dissipation. And then finally, new Tesla Model Y that came out last year. There's a whole bunch of thermal performance and engineering in this particular device. For example, the batteries are air-cooled, and the cabin HVAC is air-cooled for obvious reasons. But then things like the charging inverter, the IGBTs for motor control, and the actual sensor fusion box, the autonomous driving box, those are all liquid-cooled. So you've got a combination of air and liquid cooling going on. The liquid cooling's on a common loop. So a lot of things in here needed to be kept cool. And again, we're dissipating all of that into the atmosphere. But the nice thing about a vehicle is that it's moving. So you've got that nice forced convection through the radiators and the heatsink fins to keep things cool. Okay, but all of these products use innovative ways to manage heat, dissipate heat, and like I said, I'm sure you all have one of these, at least one of these devices. Hopefully you got a Tesla. All right, so I want to talk a little bit about Thermodynamics 101. This is going to be going back to sort of, some of the topics you covered in high school maybe, but just to kind of reiterate, and I'm going to be discussing some of these concepts as we go through. So first of all is conduction. So conduction is by far the most dominant heat transfer mechanism, okay, and it's characterized by Fourier's law. Okay, so you can see here the amount of heat transmitted is equal to the thermal conductivity times the area multiplied by the delta T and the thickness divided by the thickness of the actual piece of material. Okay, so imagine if this is an aluminum block, we have an area, we have a thickness, we have a conductivity, and this is the most critical factor. This is a material property which defines conduction. Okay, and if we have a look at some common values of thermal conductivity, which is measured in watts per meter Kelvin, you can see on the screen some good ones and some not great ones. Okay, so common heat spreaders in electronics are aluminum. Okay, so aluminum alloys can range from about 120 to over 200 watts per meter Kelvin. It's cheap. You can extrude it. You can machine it. It's very well understood, and most electronics will have some sort of aluminum there for thermal management. The other one we see a lot of is copper. Okay, copper is by far the most the highest thermal conductivity, almost twice that of aluminum. And the downside to copper is it's much more expensive. Okay, so you're talking 3, 4, 5x the cost of the similar amount of aluminum. So it's used sparingly, but when you really have big thermal issues, then the copper is the way to go. I mean, you can go up to gold if you want, which is even higher, but that's not realistic. And then on the other hand, we have insulators. So what you'll notice about thermoplastics, polypropylene, polyethylene, ABS, all of these other products that you might be using for things like enclosures, they're all sub 1 watt per meter Kelvin, even sub 0.5 really, realistically, and the good thing about these insulators is they're dielectrics. They will not conduct electricity, so there's no problems with shorting or grounding or anything like that. And if you want to insulate something, make sure something's not too hot to touch. You want to use some sort of plastic, yeah, it's again, it's a combination of the two that we see in modern day electronics. All right, next one is convection. So convection is characterized by Newton's law of cooling. So in this equation, so convection is when we have heat transfer from a solid into a moving fluid. Okay, so this time it's the area times the delta T multiplied by H. H is the heat transfer coefficient measured in watts per meter squared Kelvin. Okay, and it's a function of the fluid properties. Remember, a fluid can be a liquid or a gas. It is a function of the geometry. Okay, so how if you have narrow channels that the air has to squeeze down, it has to increase in velocity, and also the convection type, natural or forced convection. So for air cooling, for natural convection air cooling, oh, actually, we've got both here. So for natural convection, the range is, 3 to 12 watts per meter square Kelvin. Typically about 5 I would typically use, if I wanted to estimate roughly how much, if I wanted to do a hand calculation to estimate roughly how much natural convection cooling that I'm getting, I would use 5 watts per meter square Kelvin. For forced convection, so when you have fans or blowers or some sort of air mover, then you're talking maybe 50 watts per meter square Kelvin. Okay, so an order of magnitude difference when you go to that forced convection. Okay, and when you're trying to cool things with natural convection, you want to make sure that the long edge is face down. That means that it's getting the most cool air. And if it has to be horizontal, you want it to be placed down where the air can hit it and then rise upwards against gravity. You don't want, cool air hitting it from underneath, because that really restricts where that air can go. You want to kind of develop that plume by having the electronics vertical and the air being able to rise above it. Okay, so when it comes to forced convection, i.e. moving air, then we need to consider the boundary layer. Okay, so a boundary layer is something that forms whenever a fluid passes over a piece of geometry, whether it be a flat plate or a heat sink or some sort of enclosure. There's always a boundary layer that forms. Now, there's 3 stages of a boundary layer. It can be laminar, transitional, or turbulent. Okay, and they all have their various pros and cons, but it always develops in this way. Flow always starts out laminar, and then it will transition into fully turbulent flow. And how and when it transitions will be a function of the geometry, the fluid, and the Reynolds number comes into it as well. But I just wanted to make you aware of the boundary layer, or remind you of the boundary layer, because this is really, really important for heat transfer. There's also a concept of a thermal boundary layer. Okay, so remember, flow at the wall is always 0. Okay, and then it accelerates, or I shouldn't use the word accelerate. The flow will through the boundary layer become the free stream velocity, and you're going to get a boundary layer velocity profile. That's also the case for the temperature within the boundary layer. You have the free stream temperature and you have the boundary layer temperature as well. And how thick or thin that boundary layer is will determine how good your heat transfer is going to be, okay, into a moving fluid. So just bear this in mind. When we're talking about natural convection, then you always want to position your sort of heatsink fins or whatever you're trying to cool in the direction of gravity, because that's the direction the velocity will be moving and the boundary layer will be forming. Okay, so in this instance, the velocity and the temperature gradients are coupled, and the movement of fluid is a result of the buoyancy forces, the air getting less dense as it gets hotter. Because it's less dense, it moves upwards, and cooler air comes up underneath to cool it down and to replace that flow. And then finally, we have radiation. Okay, this is probably the least significant of the heat transfer mechanisms, but it's the most in certain space applications. Okay, it's important for passive cooling systems, and you can see the governing equation for radiation. I won't go into all of this, but I just wanted to point out that the biggest driver for radiation is the delta T to the power of 4. Right? So you have the T ambient minus T device to the power of 4. So if you can make that delta T as high as possible, you're going to get a lot of radiative heat transfer. Okay, and especially if you're radiating to space, so the new James Webb Space Telescope or anything on the ISS, they rely on radiative heat transfer to dissipate heat to the cosmic background radiation. Okay, which is roughly 3 degrees Kelvin. So there you've got a huge delta T to the power of 4, which means radiation, there's a lot of losses there. Okay, and radiation, along with that delta T to the power of 4, is driven by emissivity, or a surface condition. Okay, so emissivity is a function of the surface of the device. So let's look at aluminum heat sinks. So if it's polished, shiny, then you're getting maybe 0.1, right? Emissivity ranges from 0 to 1. It's a ratio against the black body, the perfect black body. Okay, but as soon as we anodize that heat sink, it goes up to 0.86, 0.9, right? So very significant difference in the emissivity, both for emission and absorption of radiation. Okay, so whenever possible, when radiation is critical, then you want to make sure that you've got as high emissivity as possible, maybe by using some sort of treatment like anodization, or even painting that surface to improve the emissivity. All right, let's talk about component and PCB modeling next. So as I mentioned earlier, components, these are the hottest part of the electronic system. And I want to introduce the concept of a thermal resistance. So a thermal resistance is a simple 1D heat transfer calculation. It's very, very simple. The units for thermal resistance is degrees C per watt. Okay, and it's calculated by doing a delta T divided by power. That's all it is. Now this delta T is a little bit trickier. What delta T's do you choose, right? So the junction temperature, that's simple. Okay, that's the hottest part of the device. And by the way, the temperature is rarely constant across the surface of the silicon, but we'll get to that. So you have the junction temperature minus TR. Do we use ambient temperature? Do we use the PCB temperature? Do we use the case temperature? Do we use some sort of arbitrary temperature that we've picked out of the air? This is a little bit trickier. So if we want to know the thermal resistance to the case, then we can do a thermal resistance calculation there. Tj minus T case divided by the power dissipation, and that's typically the electrical power that we supply to the device. Okay, junction to case, junction to ambient resistances, very easy to do that calculation. Now, where it gets a little bit trickier is when we consider what sort of environment that package is placed in. Okay, so this thermal characterization has been standardized by the Semiconductor Equipment and Materials International Consortium and the Joint Electron Device Engineering Council, JEDEC. Okay, so they have produced a series of papers which tell you the standardized way that you should be characterizing your devices. Okay, so you can control things like the case temperature, or the sort of PCB that it should be placed in. What sort of thermal test chamber should we place the device in? And we can there are standardized measurement locations and ways of measuring the junction temperature as well, and how to apply the power. So I'd recommend you to go and check out the JEDEC 51-1 paper. It's available for free online, and that will talk about how to characterize a device. So once you have that device characterized, oftentimes it becomes too heavyweight to use in in full detail, and oftentimes you might want to create something called a compact model. So a compact model in an ideal world will perform exactly as the detailed or actual chip, with a lot less calculation overhead, and maybe you want to protect your IP and not release what the internal construction of your package is. So a compact model is very useful for vendors to supply on websites, or to thermal management companies, so that it's kind of like a validated vendor characterized and blessed model that can be provided. And there's a few, there's a few of those available. We have two resistor, we have star or Delphi models, we have Delphi models with shunt resistors to increase the accuracy, and Flowtherm has what we call smart parts to generate these compact models and position them in your system so you maintain the accuracy without having to sacrifice solution time or IP disclosure. You will also have something called dynamic compact models as well. So these compact models are great at steady state. Okay, so when you just have a fixed power dissipation and you just want to see what the final resting temperature is. But when you're looking at transients, i.e., when you have a power dissipation varying with time, or you have maybe a EV drive cycle that you want to look at, where you have, again, power dissipations varying with time. That's when you need dynamic compact models. Okay, and these will allow you to get a much more accurate transient thermal response. And this is represented with a series of thermal resistances and capacitances moving away from the junction as the heat or the power encounters different resistances within the package or the conduction path out of the device. So as I mentioned, there's a few different IC package representations available. We talked about thermal resistances, theta JC, theta JB, that you might find on datasheets. You could just use a simple block model. Okay, so maybe you've got just a cube or a cuboid on a PCB, but then the question becomes, what conductivity do we use for that chip? Do we use silicon? Do we use plastic? Do we use aluminum? We need a bit of calibration there. Then moving up in the accuracy ladder, you have thermal resistor networks. These are broadly separated into two resistor or Delphi, where you have internal resistances. And then you have a fully detailed model. So this is a fully detailed package with die, lead frame, encapsulant, the whole, construction, what materials have been used, if you've got bond wires that are gold, or there's a whole lot of information in here that you might not want everyone to know about, but this is going to be the most accurate model that you can provide for modeling your ICs. So zooming out a little bit from the actual packages which we've talked about, the next thing that the heat will encounter is a PCB, a printed circuit board. Okay, this is what electrically connects all the chips together, not just chips, but things like batteries, the screen, the enclosure. There's a whole lot of things in modern electromechanical designs, but PCBs, are going to be important for electrical, and this is what the PCB team typically spends most of their time doing. So the external modes of heat transfer, there's going to be air. No matter how tightly you seal your electronics, there's going to be air in there, and that is going to be a heat transfer, convective heat transfer mechanism. But the internal modes, which is conduction, is by far the most dominant. As air is very restrictive. It's an insulator. The thermal conductivity of air is less than 1 watt per meter Kelvin. Okay, and conduction is by far the most dominant heat transfer method. So whatever we can do to increase the conductivity of the PCB is always going to bear a lot of results when it comes to thermal engineering. And let's talk a little bit about that. So let's have a look at an example of a PCB mounted plastic quad flat pack. Okay, PQFP, this is a package type. You've probably seen these, but it's got a name. It's kind of these square devices with legs that are soldered onto the surface of the PCB. There's normally a little air gap underneath, and we can understand what the heat transfer mechanisms are here. So you have conduction through the legs. Okay, the legs are what's touching the board. You also have convection and radiation across this small gap. Okay, and then you have convection away from the top surface of the board. So if we look at what the heat transfer modes are. So you can see conduction through the leads into the PCB, although that's a very small contact patch, represents 63% of the heat transfer, the conduction. Then you have 16% across that little gap at the bottom, and then maybe 20% of the heat is lost out of the top. Okay, that's very typical for a surface mount device. Okay, so anything we can do to increase the conduction is always a good thing. Let's have a look at the difference between two different PCBs. These are images, IR camera images of two different PCBs. So a TO220, this is another MOSFET type device package, okay? But one PCB has got minimum copper coverage, right? So it's got just enough copper in the board to supply power and current to the device. And then on the right-hand side, we have the same PCB, but with a copper pore around those leads to increase the spreading effect of the heat. Okay, and we can see a 20°C temperature change just by increasing the copper conductivity on the top layer of the PCB. And that comes down to the difference in the thermal conductivity. FR4, the fiber board that's used in the production of PCBs, that's got maybe a conductivity of 0.3. Copper is more like 400, right? So you're talking 4 orders of magnitude difference in the conductivity. Even a little bit of copper makes a big difference in a PCB. So how do we calculate the effective conductivities of the PCB? Again, these slides will be available afterwards, so you can kind of study this in your own time if you like. I won't go into it too much, but the main thing is the percentage copper that you include into your board. Okay, so when it comes to PCB design, the designers have quite a lot of leeway in how they design their board. One of the things they can do is increase the number of layers. Right? A board is made up of a sandwich of layers, and you can. This is a 4-layer board, but you can have 6, you can have 8. We produce some boards here at Siemens that are 64 layers. Right, some very high power. They're about an inch thick, and you know they're primarily used for electrical connectivity, but there's the added advantage for the thermal side of things: more copper, better spreading. Okay, so the number of layers, the percentage of copper on each of the layers, these all impact the thermal performance of the PCB. Some components also require a lot of current. Okay, so I'm thinking power devices like IGBTs, MOSFETs. When you're switching a lot of current, or you require maybe 50, 100 amps running through some traces, then there are self-heating effects which may come into play. It's called joule heating. Okay, so joule heating occurs when you have current, maybe the cross-sectional area of those traces gets very thin and necks down. That's where you're going to see heating, simply due to the fact that you've got current flow in those traces. So you want to make sure that you don't have any hotspots due to joule heating. And FR4, the most common laminate, fiberboard laminate used in PCB construction, will glass transition at about 110°C. So as soon as that happens, the FR4 becomes brittle. It can crack. It can actually fail and cause shorting. So you need to be careful of very high current carrying lines within your board, because there can be self-heating effects within the PCB itself. All right, Dan, at this point, let's introduce poll question number 3, please.
Great. Richard, we did skip number 2. Would you like me to bring that one up as well?
I'm sorry. I'm sorry. Yeah, maybe we can just do 2 real quick.
Yeah, you were in such a flow, with all the knowledge you were dropping about fundamentals that I didn't want to get you away from it. So I'm going to quickly share the one for number 2 attendees. It should be on your screen right now. So when do you, in your process, consider thermal design? A, upfront from the start. B, late stage during testing. C, when there are field failures. Or D, what's thermal engineering, which Richard has been going through with us. So we'll give you all about 15 seconds to just go ahead and, again, give us your best guess. In the meantime, Richard, I must say the fundamental class has been really refreshing, the concepts you're sharing and bringing up again. We're seeing some questions coming in relation to what you've been sharing, which we've been answering throughout. So for the attendees, if you have additional questions, please don't hesitate to continue sharing them. And I'll also say that the examples you gave on cutting edge thermal management strategies was very refreshing and provided great insight on devices we use every day but don't really think about what sort of thermal management strategies are there. So lots of great learning already. So with that, I'm going to go ahead and close this poll. Just to share with the audience very quickly, again, very few of you are still learning about thermal engineering. It's great. The majority are looking at thermal design from the upfront, which is definitely the right approach. There's a couple that are seeing it, in late stage or with failures, which again, the more we front loaded, the more supportive and the better it's going to be in terms of avoiding more costly overruns later on. So I did want to share that. And with that, I'm going to go ahead and put forward the third polling question, which should be there right now. So again, it relates to the PCB design that we've been going over. And the question is as follows: does the PCB team design any of the following into their designs for thermal reasons? And go ahead and select one. So thermal vias, copper pores, thick ground, power planes, or D, all of the above. And again, you use your best guess. If you're not 100% sure, that's fine. Again, it helps us understand what are some of the thermal design strategies being used for the PCB team.
Yeah, more and more I'm seeing, the PCB team and the mechanical team working together to design these thermal considerations into the PCB, because devices are getting smaller and smaller, more and more powerful. No one wants fans in their devices, so you have to now increase conduction with the actual layout design of the board.
Right, and the importance of the collaboration piece you just mentioned. I know we're not going to go into much detail today, but also a pivotal piece in terms of how we're seeing the different industries and teams trend when it comes to PCB design. So I'm going to go ahead and close this poll just to share very quickly what we're seeing. Majority of respondents shared all of the above in terms of what they're putting into their designs for thermal reasons. B said only or majority, with copper pores, and there were a few which had thermal vias or thick ground or power planes being used. So I think, as probably expected, Richard, we do see the majority being all of the above. But again, this lines up with what we're seeing, what we're expecting. So with that, I'm going to go ahead and close that poll and pass it back to you.
All right, thanks, Dan. Yeah, that's great to hear that people are designing these things into the boards. I think it's a really, really important part of electronics design. And in the third session, we're going to be focusing very heavily on PCB modeling. And the second session next week is going to be IC modeling. So we'll dive into these devices a little bit more next week. All right, let's talk about heat sinks. Okay, I'm sure we've all heard of heat sinks and we know what they do, but let's talk about some of the theory behind heat sinks. So heat sinks are effectively heat exchangers which are maximizing the surface area and ideally maximizing the heat transfer coefficient. They are convection promoting devices. So we can see on the screen here some typical H values for different fluids. So air, by far the most common for use in heat sinks. You can see maybe 5 to 20 to maybe even up to I'd say maybe 30 watts per meter square Kelvin. And when we move to air and forced convection, it can be anything from 10 to maybe 200. Typical value there. And then we start to get into more exotic cooling methods, fluorochemical vapors, engineered fluids, transformer oil for liquid cooling. Water's great, look at water, maybe 200, 300 to up to 10,000. So huge there, depending on how you implement water cooling. And then you can even go as far as things like pool boiling. I wouldn't want to use water there. I'd probably use some sort of fluorochemical liquid or engineered liquid for boiling. And we'll talk about that towards the end as well. But this gives you just a range of the H's that we see for heat sinks out there. So when it comes to heat sinks, as I mentioned, the convective heat transfer is proportional to the exposed surface area. So this is a very quick hand calculation you can do. You saw earlier the Q equals HA times delta T. So if we know the delta T we're trying to get to and we know the power dissipation, we can take a stab at the H based on this chart. We know roughly what the surface area of the heat sink should be. Okay. Then we also need to take into account thermal radiation if we're talking about natural convection. Okay, for forced convection radiation can most of the time be discounted and we don't need to worry about it. But natural convection is very important. But the interesting thing about radiation with heat sinks is that, in the middle of the heat sink, the fins are just radiating to each other. There's not much delta T, so there's almost no radiation. But the outer fins or the top faces, they're going to be radiating out to the environment and the ambient. Okay, so yeah, no brainer, increase the surface area and increase the heat transfer coefficient we can by using air movers or using a different fluid or doing something to increase that H and promote heat transfer. So I like to introduce the concept of talking about a thermal budget at this point. Okay, so remember, we know what the maximum temperature allowable on the chip is, roughly 120 degrees C. We know what the ambient temperature is, about 40. So we can fit in thermal resistances between the chip and the ambient and introduce a thermal budget. Okay, so you have maybe chip to substrate thermal resistance, substrate to case thermal resistance, case to heatsink thermal resistance, and then heatsink to ambient air thermal resistance. Okay, so a lot of heatsink manufacturers will provide thermal resistance calculations on their data sheets, and you can use that to kind of work out, what sort of heatsink that you should select. A lower thermal resistance, the better. That means it promotes that spreading and the convective heat transfer. But oftentimes you're more limited by mechanical constraints. Does it fit in the box? Does it fit in the phone? That's why I find mostly drives heatsink selection at this stage. But yeah, think about the thermal budget, okay? And some of these resistances will be fixed, but things like the heatsink, this is something that you can play with and give yourself a bit of headroom towards the end to just give you a margin of safety when it comes to thermal resistance calculations. Okay, so natural convection heat sinks. So general principles, again, you'll find manufacturer information on data sheets for thermal resistance. The orientation is very, very important, okay? So if gravity is pointing down, you wanna make sure your fins are aligned with gravity. We wanna make it as easy as possible for air to get through that heat sink, okay? Surface finish, anodizing, we saw earlier for radiation, important. So we can perform some optimization on heat sinks, right? We can play with things like fin height, fin length, what the spacing between the fins is going to be. And this is going to get into your optimization, okay? You can pick a heat sink that fits in a certain space, but is there a better one? Is there a worse one? By how much? And this is where simulation really comes in and allows you to, work out what the best heat sink is going to be. It's not necessarily the one with the most fins or the one with the highest surface area, because as you can see here, when you have a bigger spacing, you're going to get more airflow, right? If they're too close together, it's too restrictive. You're going to get minimal airflow. So there is a balance to be struck here when it comes to selecting a heat sink. It's not always just about the thermal resistance or the surface area calculation. You've got to take into account the airflow, the orientation, surface finish. There's a lot going on. So just some basic tips and advice for orientation of heat sinks. You want them aligned with gravity, as I just mentioned, if possible. If they have to be flat, then you're going to see maybe a 20% increase in temperature, okay, due to if you use the same heat sink in both orientations. And you want to keep the long edge sort of perpendicular to gravity if possible, okay? And you want to avoid long fins as much as possible, and I'll talk about why that is in just a minute. And surface finish, we've talked about that. So what we can do with heat sinks is optimize the fin length. So remember, we talked about the boundary layer. As the air rises up through the heat sink fin, the boundary layer is going to grow. It's going to go from laminar, transitional into turbulent. If it's natural convection, it probably won't go into turbulent airflow unless there's something strange going on there. But it's always going to be against gravity, and the boundary layer is going to grow. So at some point, making the fin longer is going to have minimal effect because the boundary layer is so thick, not only the flow boundary layer, but the thermal boundary layer, which means that it just cannot dump heat into the air because the delta T is so low, which means that your heat transfer coefficient goes right down, and effectively you got a dead zone in your heat sink. There's also fin spacing, not just the length, but the fin spacing is important. Again, we got the fin spacing between the heatsink fins. The air is going to come up, the boundary layer is going to grow, and at some point, these boundary layers can actually touch. And as soon as they touch, you're going to get zero airflow at that point. Okay, we know that there's reduced velocities in boundary layers. This is the free stream velocity. If they touch, it's game over for that portion of the heat sink. It's not going to be moving any heat into the air unless you increase that velocity. As you increase the velocity, the boundary layer is going to get thinner. It'll still grow, but it'll be thinner. Now, so here's a empirical calculation you can use for estimating boundary layer thickness. Again, I wouldn't worry about this too much. Sort of the rule of thumb is generally the spacing is similar to the thickness of the fins, right? So if you've got 1 mil fin thickness, you're going to have about a 1 mil gap in between the fins as well. That's pretty typical. Okay, forced convection heat sink. So we were just talking about natural. So forced convection, what we need to compete with now is the hydraulic loss through the heat sink. What do I mean by that? So there's going to be a resistance to movement of air as we try and force more and more air through that heat sink, right? So as the flow rate goes up, the pressure loss goes up. Okay, this is a relationship called the pressure loss. Okay, and we need to combat that with a fan. Now, the flip side to that is, as we increase the airflow through the device, the thermal resistance of the heatsink comes down as well. Okay, so you can see it plateaus out. So, maybe anything over 60 cubic meters an hour, you're not going to see much difference. As you double that, you're going to see maybe, sub 5% decrease in thermal resistance. But there is a decrease because of that higher velocity, thinner boundary layers, more mixing going on in the boundary layer as it's turbulent flow. But then the downside is there's more resistance, you're going to need a bigger fan. So you need to strike a balance between the pressure loss and the thermal resistance. So other things to consider with forced convection heat sinks is the streamwise length should not be too excessive. Okay, as you force more and more air down the device, then again, the boundary layer is going to grow. It's going to be less effective because the air has been warmed up. Let's look at this one, for example. So we have some power devices that are clipped to the side of this extruded heatsink. A fan is forcing air down the middle. The first one is going to get the nice cool air. The last one's got all this dirty heated air with the thick boundary layers from the other guys. So this is going to perform the worst by far. So you don't want to make things too excessive. You can do things like machine slots in heat sinks to break up the boundary layer, promote newer, fresher air from the free stream to be introduced back into the into the boundary layer and between the fins. Okay, the orientation of the fins is really, really important to the incident airflow. Okay, again, you want it going along with the airflow. No point putting a perpendicular fin in there; it'll just hit that and deflect around the rest of the heatsink. Surface finish is not important. Again, radiation is minimal in this instance, and the air velocity within your heatsink is going to be determined by the volumetric flow rate divided by the cross-sectional area. Okay, so a fan will supply so many CFM or so many liters per minute. You need to divide that by the surface area that air can travel through, and that's going to give you your local velocity, your average local velocity within the heatsink itself. You need to use simulation if you want to then go down into the actual fins and look at the more localized velocities. I'm just going to make sure that I haven't skipped. Oh no, it's the next slide. Okay. All right. So forced convection heat sinks. So again, a little bit like chips, there's no standard method for characterizing a heat sink. JEDEC haven't come up with a standardized methodology. It's really up to manufacturers to determine how that data is provided on data sheets. And manufacturers obviously want to look as good as possible, so they may use, shall we say, generous testing methodologies to ensure that the numbers look good. So I'd always take datasheet values with just a pinch of salt. Okay, so their thermal resistance and pressure drop calculations are typically performed. Tests are typically performed in a wind tunnel. Okay, you have a heater or a chip underneath the heatsink. The heatsink is placed in the tunnel. We measure the pressure loss, okay, and we measure the delta T of the air either side or the power consumption of the actual heater, right, to maintain a certain temperature. And then from that, we can change the velocities and ramp it up, and then grab those two curves that we saw earlier. Okay, so the thermal calculation would just be the delta T divided by the power that we supply to the heater. And then the delta P is just the pressure readings either side at a certain velocity or flow rate. And comparison between heat sinks is tricky because, again, the testing methodology has not been standardized. There is a proposed American Society of Mechanical Engineers paper out there, but it has not been adopted yet. All right, so Dan, at this point, let's ask poll question number 4.
Great. This is very insightful on heat sinks. Gone ahead and shared the poll. Attendees should be seeing it on their screen right now. So when selecting heat sinks, what is the dominant selection criteria? A, thermal performance. B, it mechanically fits. C, it's cheap and available. D, physical appearance. While we get those answers coming in, Richard, our team's been answering questions on the back end that we've been seeing. There is one that we'd like to flag for you. I do believe you're going to cover it in a follow-up session. The question is, what is the selection criteria in using one of the methods for the 4 types of the IC package representations? I just wanted to share it with you now in case you want to cover it briefly now or towards the end of the presentation, but this is one we thought it might be helpful for you to address.
Sure, yeah, so the 4 different methods, so there's the thermal resistance, there's the block method, there's a resistor, and then there's the detailed. Which one do you use? I would say it comes down to availability. Okay, if a manufacturer provides a detailed model or a Delphi model, use it. If it's a high power component that's dissipating a lot of heat, Intel, AMD, Qualcomm, they will provide those flow therm models on their website. Use them. If it's a passive device, a resistor, capacitor, maybe it's something that's is not going to be thermally important. It's not got enough heat on it. You can just use a block or a thermal resistance method in the simulation. So yeah, just to answer that in a word, I would say availability. Use the best fidelity model that you have available.
Excellent. Appreciate that succinct answer. And again, I do know we'll cover it in greater detail in follow-up sessions, but wanted to address that right away. And wrapping up the poll, again, if we're looking at the dominant selection criteria, the key result or the majority of the answers really going into being thermal performance along the lines of expectations, though a large number of attendees also talked about being able to have that mechanical fit. So, Richard, I know you touched on it briefly, but just in terms of connection and collaboration between mechanical electrical design teams, I think it's interesting that we're seeing it represented in some of the polling answers. But I'm going to go ahead and stop the poll and pass it back to you now to keep moving us forward.
Yep, agreed. And that's kind of what I was trying to get to earlier. You know, thermal engineering typically is done where I see it being done more than not is late stage. Once everything's been signed off, the enclosure's been signed off, the PCB's been signed off, then you have to try and cram a heatsink or a heat spreader in there. That's when it starts to get expensive, tricky, and you have to resort to some more complex ways of pulling the heat out. But we'll talk about that in next week and the week after session. All right. So in summary, use thermal resistance calculations to select a heatsink. Natural convection fin arrays, you know, fin length and temperature and orientation considerations. For forced convection, again, fin length, air velocity calculations that you should be doing, and again, orientation and finish. Bypass calculations, how they're measured in heat in wind tunnels, and you know how you can use that data from data sheets and augment that with simulation to give a much better final performance of the heatsink. All right, so last section, we're going to be talking about fans. Okay, no one likes fans, but sometimes they are a necessary evil, especially if it's a piece of electronics hardware that doesn't move around. Maybe it's in a data center with nice, cool, clean, dust-free air. Then, you know, fans are, you know, a viable option. There's a couple of types of fans. Axial flow. These are the ones that we're most familiar with. They're thin. They move air. They come in one side and they go out the other side in the axial direction. There's no direction change there. And they can deliver a high flow rate against a low pressure. Okay, and we'll talk about this a bit more in a second. But then you also have radial fans. So these are a little bit different. These are called blowers. And the air comes in the axial direction of the fan, but exits perpendicularly. Okay, and this can deliver a lower flow rate, but a much higher pressure. Okay, so the actual air that comes out of it has much higher pressure. It can overcome more resistance, like densely packed heatsink fins. Right, you want to use a blower in that instance. So let's talk about selection and calculations. So the fan characteristic, on every data sheet for a fan, you'll find a fan curve. A fan curve is this solid line on this graph here. It is the flow rate versus the static pressure that it can deliver. Okay, so if there is zero pressure difference across a fan, it will blow at the highest possible flow rate. In this case, 40 cubic meters per hour. Okay, if there is a large pressure loss, then that flow rate will come down. And this fan curve characterizes that fan. Okay, so if you have a low resistance system, again, this is that same curve that we saw earlier on the heat sinks, the resistance versus the flow rate, then the crossing point is where the flow rate is. Okay, if it's a high resistance system, you're going to have a lower flow rate. Right? So you can overlay these two graphs on top of each other and understand what the operating point of the fan and the system is going to be. And the system, it might not just be a heat sink. There could be further components downstream that impede airflow and cause resistance to airflow. So with axial fans, again, low pressure, high flow, there is a recommended range. Let me just go back a slide. There's a recommended range on the fan curve. It's typically down here in the later, around the 80% mark of the fan curve down here. This is really where you want to size your fan. This will be a good point. If the low resistance system, this is where you want it to be. As you get more and more resistive, this is a bad selection point. I would choose a different fan at this instance to make it more in the late 80% of of the fan. This is where it's designed to operate. This is where it's the most efficient, it's the quietest, and it's going to last the longest as well. Okay, so something you might not know about fans is as the flow rate actually decreases, okay, then you're going to see the shape of the airflow coming out of this fan change. There's actually a conical sort of shape on the outlet of a fan, and the angle of that will change based on what the delta P across that fan is going to be. As the delta P goes up, the flow rate goes down, remember, okay? So if we are operating in that late 80% range of the fan, we have nice straight air like this, okay, low resistance to flow. As we start to increase the delta P, the flow actually starts to kind of bow outwards, okay, and you're not going to get that nice uniform flow on the outlet of the fan. It starts to kind of move outwards as it resists the pressure, because it's higher pressure on this side, lower pressure on this side, which changes the characteristics of the fan. So if you were to place a heatsink right in front of here, it might not be doing much because the air might be being pushed to the sides because of that high delta P. Okay, so at this point, I would make sure that I choose a bigger fan to ensure that the flow is more normalized at the outlet. So a couple of things to consider for fan-cooled systems. Things like dust ingress. Okay, this is a bad thing. It coats the inside of components. It can look bad. It can, you know, if there's metallic shavings, it can short things out. It's very problematic. Fan life, especially the bearings, if dust gets into those, big problem. They can go down, and you know it's not a quick job to replace fans. You might have to, well, you almost certainly have to open up the server and swap those out. There's also the concept of downstream heating as well. Okay, so as the air is heated through the device, the air is going to get hotter, the density of the air goes down, which affects the fan performance. The fan curve will be different than ambient air. The fan inlet conditions are really important. What's actually behind the fan? Is there a grill? Is there something blocking the airflow entering the fan? And then air quality. Okay, so acoustic is important. You know, anything above, I would say, 3,000, 2,500, 3,000 RPM, it's going to be annoying. If you've ever been in a data center, it's really loud in there, and that's all the fans making sure that everything is cool. Okay, and balancing all of these factors governs whether the fan will be at the inlet or outlet, and let's talk about that. Oop. Okay, so here's an electronic system. Imagine this is a server. Okay, we've got electronics in front and behind of the fan, and the fan is in the middle in this instance, and we have axial flow from left to right. What a fan does, it pulls air from one side, blows it out the other, and as a result of that, the air pressure behind the fan is lower than the air pressure in front of it. This is what a fan does when it moves the air. It changes the pressure and moves the airflow around. So there's benefits to having negative and positive pressure within the system. Go down. So at this point, Dan, maybe we can just flash up question number 5, and then I'll move on because I've just got a little bit more to do.
Sounds good. This one's a pretty straightforward yes or no, and again, think of just the explanation provided by Richard on just fan design, fan related strategy. So, did the products you design incorporate air movers and slash blowers? Simple yes or no would suffice. So, again, we'll give it another 10 seconds or so. Feel free to give your best guess if you're unaware. And again, just for the attendees, I recommend you continue sharing your questions as you have them throughout. All right. I'm going to go ahead and close it at this point. Just a quick share, Richard. Surprisingly enough, we almost have a near exact split between people designing products with or without movers. So I think it's interesting that some will benefit from strategy, others may consider it in terms of how they design their products moving forward. So it's good for us to note in terms of the attendees in future sessions. But with that, I'll pass it back to you.
All right, great, thank you. All right, let's continue with fans. So one of the issues with fan location, where the fan is positioned in the system, is dust ingress. Okay, so think about what I just talked about with the pressure here. So if we have negative pressure, air is being sucked in to the system. If we have positive pressure, air is being pushed out of the system. This is just, you know, the pressure difference, a bit like temperature difference. Air wants to go to equalize the pressure as quickly as possible. Okay, so if we have the fan at the inlet, what we end up with is a pressurized system. The air on the inside of the box is slightly higher than the outside. Okay, so air will be forced out of any apertures. And the benefit of that is only a single filter is required at the fan inlet. You don't have to worry about sealing all the gaps in there to stop air and dust getting into the system. And there's some other benefits as well I'll talk about in just a second. Now, if we have if we position our fan at the outlet, then that means that the pressure is slightly lower inside the box. So air will be pulled into the system through the slots that we want, but also potentially other slots or, you know, gaps in the sheet metal that we don't want. And dust will accumulate in those places as well. So we do need to think about sealing these carefully and filtering the incoming air when you have a pull-through system with a fan at the outlet. Okay, just something to bear in mind. And as you can see, fans can block up heat sink passages, it can gum up fans, get in the bearings, it smells, it looks bad, it's contamination, it's dead skin, it's gross. We don't want that. So yeah, my recommendation is positioning the fan at the inlet to have that pressurized system. So temperature effects, I just touched on this a second ago, but when you get a data sheet for a fan and you look at the fan curve, it will always tell you what temperature and maybe not altitude, but that's assumed sea level, but what temperature the air was tested at, okay? And air can change density quite significantly with temperature, okay? And that can have the effect of shifting the curve. If there's less air, then there's going to be less flow rate, right? So there could be a modified fan curve that we need to take into account due to the heated air. So if you have your fan at the outlet, you've got warmer air, it's going to be less effective. So that's another bad thing about having the fan at the outlet. Another thing is objects blocking the fan inlet as well, right? So just a very crude drawing, but here's my fan. Maybe there's something like a power supply, maybe partially obstructing the fan. That can have a huge impact on the fan curve as well. You know, having some sort of resistance and asymmetrical resistance on the inlet to the fan can really affect the fan curve and make it perform a lot worse than it should be doing. So just be careful of what you place upstream and downstream of the fan, and stop any sort of, you know, asymmetrical problems which causes air to not enter the fan smoothly. Okay, so in summary, if we have a push-through system, then there's minimal dust ingress. The temperature on the inlet of the fan is ambient. There is downstream heating, so the components further down the stream are going to get you know, heated by the ones before it, and the overall cooling effect is generally good. I guess one of the issues is the airflow. If we look at across the cross section of the electronics, the airflow is unsteady. We do get these jets, high velocity jets coming off the fan, which may or may not be good, but we don't have that uniform velocity across the surface of the cross section of the electronics. Okay, so that unsteady could create dead zones downstream, you know, immediately left or right of the fan. That can potentially cause problems. And then if we have the fan at the outlet, you know, all the cons there, But the only benefit really is that you're going to get much more uniform airflow, right? So if you look at the velocity profile of the air in cross section, it'll be a lot more uniform because we're sucking the air through rather than pushing it through. And that sometimes can be beneficial if you've got sort of, uniformly cluttered electronics enclosure with fans. Just something to bear in mind. All right, I think this is getting on to my last slide. But in conclusion, and key takeaways. So the first one, leave as much copper in the PCB structure as possible. You want to have at least one single nearly continuous layer in the structure. This can be a ground plane, a power plane, something in the board to increase the copper, promote conduction, promote spreading. We really want to get those point temperatures, the high hot spots on the board away by introducing copper into the board. We want to disrupt, number two, we want to disrupt the development of boundary layers and heat sinks, minimize the characteristic length, right? We want to, keep the boundary layer as thin as possible. We want to keep the heat sink fins as short as possible, promote convective heat transfer, and make your heat sinks as effective as possible. Thirdly, locate critical components close to the coolest air and beware of conductive interaction and downstream heating. If you have a row of high power components, they can actually heat each other and create like one giant hotspot. So you might be better off moving them apart or staggering them somehow so you're not getting sort of cross conduction, especially if they're not all uniform power dissipations. And then finally, position the fan upstream of the board to increase mixing in the airflow to disrupt the boundary layers and stop dust ingress as well. So yeah, selecting the fan upstream has got a lot of benefits to pressurizing your electronic systems. All right, if you're interested in this topic, then there is a lot more out there. If you want to do some further reading, we haven't even touched on heat pipes or vapor chambers. There's a lot of hand calculations and complexities involved in incorporating these into your electronics. These are two-phase devices. Thermal interface materials, thermal grease. We haven't touched on that really. Synthetic jets. These are really cool. These use piezoelectric elements to create airflow without actually sucking in air from behind. They actually create jets using, vibrating elements in the kilohertz range. Liquid cooling, Peltier devices, two-phase immersion. This is really cool. You're using engineered fluids, fluorocarbons, to actually boil liquid and cause very, very high rates of heat transfer there. And then phase change materials as well. All things that we could talk for hours on, but if you're interested, I'd recommend reading into this a little bit more. There's a whole world out there for electronics cooling. And with that, we're almost at the end, and we'll just do the final poll question number 6, please, Dan.
Perfect. That was wonderful summary, and appreciate you sharing the additional material as well, Richard, or areas where we can explore. For all the attendees, our final polling question for today: how does your company ensure thermal compliance? We put 4 options out for you. A, physical testing. B, computer simulation. C, outsourced. Or D, no thermal analysis performed. So we'd appreciate your insights. Richard will just do a quick review of the upcoming sessions we have, and you'll see how this all ties in. And Richard, as we collect some responses, we have seen more questions come in. There's one that I wanted to also share just from that list. I know our team's answering them, but one for you. Most of our products are in a sealed plastic enclosures for IP protection purposes. In this scenario, what would be the best practice for cooling such devices? If you had any thoughts on that.
I come across this one a lot. So, when you have everything sealed up with O-rings and gaskets, so water, dust, nasty stuff doesn't get in. You have an internal air volume, you have the external air volume, and you're normally reduced to using plastics there. What I'd recommend is using maybe a higher conductivity polymer if possible. There's some new materials out there that can really conduct the heat away, and think about how the device is going to be orientated or mounted, right? You want to use gravity because natural convection is going to dominate inside the box. You're going to get convection currents moving against gravity. So anything that you can do to have an air volume at the top, or maybe more critical components towards the bottom, that's going to benefit things. Okay, so yeah,
No,
this
that was
is
excellent. I really appreciate that thought, Richard. Just a point, as you can see, a lot of physical testing, computer simulation. We did get a comment with people saying that even though we're offering one option, their companies tend to do more than one. We appreciate that. We'll factor that into our upcoming presentations and polling questions. In this case, it's great if you shared your best guess. So with that, Richard, just off to you as we wrap the session up.
Yep, I think that's all of my material. So Dan, I don't know if you want to do the last few slides.
Excellent, will do. I'm just going to go ahead and scan the questions one more time, Richard, as we've been going through quite a few of them. We did have a question around, bear with me for 1 second. When we go to the fans, so there's two parts to this. One is is there a change of thermal performance with inland and outland fans? And the other part is, what about the heat supplied by the inlet fan? I don't know if you can touch on this one quickly.
Yeah, sure. So if you have the fan on the outlet, you have that air you've got the warmer air that you're dealing with. So the flow rate through your device typically tends to be lower, which will result in higher temperatures. And then, sorry, repeat the second part of that question, please, Dan.
The second part being, what about the heat supplied by the inlet fan?
Oh, okay, yeah. So, fans do consume a little bit of power, maybe 2 or 3 watts, something like that. Fans are self-cooling. They're moving enough air around them that they are self-cooling. It will heat up the incoming air a little bit, but it'll be negligible compared to how much power has been dissipated in the box itself. So, I think you can probably ignore that.
Very, very well said. With that, we'll look to wrap up. Again, there may be a few questions we didn't get to. We will circle back on those. In terms of the series, as we mentioned, this was the first session. Really, we want to show you end-to-end when it comes to managing thermal performance or factoring in thermal conditions. So today we talked about the fundamentals. Hopefully it was a good refresher or perhaps something new for you to learn. Next week, again, same time, same mechanism, we'll be going over thermal performances of IC packages. The week after, we'll talk about PCB level thermal analysis. And then our final session on March 23rd will be on thermal test and validation. So we look forward to seeing you for those sessions. The material will be provided prior to the end of this week. And we'll look to make available what was presented. And in case we have any questions that we're missing, we'll aim to address those as well. So if you have additional questions, please don't hesitate to reach out to us. Richard, once again, big thank you to you for putting this material together. And if there's anything else, people don't hesitate to reach out to us. Thank you all so much for your time.
Thank you, everyone. Speak to you next week.